Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we will perform the velocity feedback for the position control of the DC motor. So here the DC motor will follow the input square wave trajectory. This is the circuit diagram. Here you can see at the input side we are having the square wave input that is provided through this potentiometer, which is the variable resistor, and that is further provided to the operational amplifier. This is a theta I, the input square wave. We are having a theta naught. This is the theta naught, and this is the output rotary potentiometer. This is the position of the DC motor shaft, and these two signals here are added together, and as a result there is the output signal. This is the error signal. Here we are having operation amplifier used as a summer and as a gain controller. So we are having different values. The gain here, when the output resistor is 100 by 100, so the gain is 1. When the output feedback value of the resistor is 330, so the gain is having 3.3. And when the feedback value is 1 mega ohm, so the gain is increased by 10 times. That is further provided to the potentiometer, and the same is further provided, signal is provided to the servo amplifier. So this is the example here, and this servo amplifier is connected to the DC motor. The DC motor is connected with the output shaft is further connected to the we are having the tacho unit. This is the tacho unit, and this tacho generator this is the tacho unit, and that is further connected. That signal will be further connected to the input of the operational amplifier. So this is how it looks like on the machine. We are having this is the DC motor at the back of, this is the DC motor here, and at the shaft of the DC motor we are having this aluminum disc, which is the rotating disc, and further we are having the tachometer, which is a tacho generator, which gives the speed proportional to the speed of this DC motor. And we are having, this is the input rotary potentiometer. In this case we will not use it. We will apply square wave in place of this input rotary potentiometer. Well, by means of the we are having the shaft position is connected by means of the gears to the output rotary potentiometer. This is how it looks like on the machine. We are having the square wave input connected through the input rotary potentiometer, variable resistor, and we are having all the input resistors are 100, 100 and 100, where the feedback values of the resistors are 100, 330 and 1 mega ohm, and that will be further connected to the servo amplifier, and that is servo amplifier is connected to the tacho unit. So this is the tacho generator, and this signal will be feedback here to the input side. Okay, so dear students, this is the whole setup on the machine, on the analog servo fundamental trainer. We are having the square wave that is provided over here on the analog unit, and that is further applied through this potentiometer here. This is the connection for the oscilloscope on this one, and the input wave can be seen on the oscilloscope as well. The blue signal, that is the input square wave. Initially we have the feedback resistance is 100, so the gain of the overall gain of the system is 1. Now we are having this is the output that is coming from the tacho generator, and that is provided to this potentiometer, and through this potentiometer we can apply the velocity feedback, and that is further feedback to the input side. So this is the input side, where this is the tacho input. This is the position output rotary potentiometer, and this one is the input square wave, where all these three signals are added together and further provided to the servo amplifier and into DC motor. So in this case, you can see here, this is the response. The yellow is the response of the DC motor, and it can be seen here on the motor. We can similarly change the frequency of the machine as well here. So now I am applying the the velocity feedback, I mean this potentiometer here, so you can see I'm just replying, and the response of the motor will be very smooth. So you can see here the difference. Now the DC motor is following exactly the square wave input. So by further, let me decrease the velocity feedback again to 0, and I'm increasing the gain. For example, if there is some steady state error in the system, so that steady state error can be eliminated. So by increasing the gain to 3.3, transients are induced in the system, you can see here, and these transients can be further improved by velocity feedback, where by means of the velocity feedback these transients are differentiated. And keep in mind, dear students, that this example is the feedback compensation, where the controller is employed in the feedback. So you can see here it's very smooth response. The input square wave that is followed by the DC motor. On the other hand, you can see here this is the response of the DC motor. This is output rotary potentiometer, where it is very smooth. You can see here positive cycle. This is the positive cycle, and this is the negative cycle. It will be, this is the negative cycle. Now further increasing the gain to 10, you can see here again. Let me decrease the velocity feedback to 0. So you can see here there are transients in the square wave, right? You can see this is the response of the DC motor, and again you can see here this is the aluminum disc, and this aluminum disc here is the shaft is disconnected by gear. This is the output rotary potentiometer. This is the shaft position, and you can see here the transients and oscillation in the motor. How much the motor is stressful. There are many stresses acting at the shaft of the DC motor, so we have to eliminate those oscillation. I'm applying the velocity feedback, and you can see here that by implying this is the velocity feedback, I have increased I have applied the velocity feedback, and you can see here this is the response is very much smooth, and it is perfectly follow the DC motor. The servo motor is perfectly following the input square wave without any oscillation and without any transients. So thank you.